A very good morning and welcome to you all for this wonderful occasion. I'd like to start by acknowledging the traditional owners of the land on which we're meeting this morning, the Ngunnawal and the Ngambri people. It's upon their ancestral land that the Australian Academy of Science is built. And as we share our knowledge, our teaching, our learning and research practices, may we also pay respect to the knowledge that's embedded forever within the Aboriginal custodianship of country. This week is particularly significant as we've celebrated National Reconciliation Week. Just yesterday, the members of the Secretariat were able to go to Old Parliament House for a First Nations visit, and we learnt more about the recent history of Aboriginal and Torres Strait Islanders in Australia. I highly recommend that to you. It was a very informative presentation by the wonderful people at Old Parliament House. My name is Anna Maria Arabia. I'm the Chief Executive here at the Australian Academy of Science, and it's my absolute privilege to be here for the 2022 Ian Wark Medal and Lecture. I warmly welcome everyone here in this aptly named place, the Ian Wark Theatre in the Shine Dome. And also welcome all those who are joining us online from around Australia and of course from around the world. We're here to present the Ian Wark Medal and hear from the 2022 recipient. I encourage you to keep an eye out on the Academy website and across our social media channels so you can nominate others or yourself for awards that you may be eligible for. We really do encourage you to think about those awards, both for yourself and for your colleagues, and to bring forward a range of nominations and applications from the broad diversity that is the Australian research sector. A couple of housekeeping items before we get started. To join the conversation on Twitter today, you can do so by using the hashtag Senden Lecture. And for those wishing to ask questions, there'll be an opportunity to do so at the conclusion of the lecture. To start the proceedings, it's now my pleasure to hand over to Professor Malcolm Sandbridge, the Academy's Vice President and Secretary for Physical Sciences. Over to you, Malcolm.
So thank you, Anna Maria. I too, of course, am delighted to be here today to present the Ian Wark Medal and hear from Professor Tim Senden, hashtag Senden Lecture. It's great to see so many ANU colleagues here who have joined us here at the Shine Dome and others from partner institutions and organisations joining online. All great scientists rely upon support of their institutions and colleagues. And so it's wonderful that so many have joined us to celebrate Tim's achievement. One of the great pleasures of my current position has been, with the Academy of Science, has been the opportunity to meet and hear from Australia's leading researchers in every field. It's always exciting to hear the incredible research in diverse fields that has been carried out across Australia, and I'm sure today will be no different from that. Each year, there are only 7 career honorific awards given by the Academy. And these are for outstanding achievements throughout a career across the spectrum of physical and biological sciences. Winning an Academy Career Honorific Award is therefore no small accomplishment. Today, we celebrate the 2022 Ian Wark Medal, and in doing so, commemorate the contributions to Australian science and industry of Sir Ian Wark. Sir Ian was a leading Australian scientist, much decorated and lauded by fellow scientists and, as his titles attest, by the broader community. He became a Fellow of the Academy in its foundation year 1954. The Ian Wark Medal and Lecture was created by the Academy in 1987, 2 years after Sir Ian's passing, through a legacy received from him and donations from his friends. Through this award, the Academy recognises research that contributes to the prosperity of Australia, where that prosperity is attained through the advancement of scientific knowledge and its application. Our 2022 Ian Wark medalist is Professor Tim Senden. Tim is a physical chemist whose pioneering research has provided new understanding of surface phenomena at the nanoscale, developing methods to quantify colloidal and molecular forces. For 2 decades, he was involved in the development of novel applications of radioactive nanoparticles for clinical use. which received strong commercial sponsorship leading to clinical trials. From the 2000s, Tim was part of a major translational activity that continues to developing a novel imaging and analysis platform based on X-ray microtomography, leading to new insights into complex granular and porous materials. This activity has greatly enhanced applications in topics spanning paper making, carbon sequestration, composites, and mineral and hydrocarbon extraction. Following an industry consortium of 23 energy companies, Lithicon was spun off and became one of the most successful ANU companies. It gives me great pleasure to now invite Professor Tim Senden to join me at the lectern to accept the Ian Wark Medal and deliver his lecture. Tim. Now I invite Tim to deliver his lecture titled How to Bake a Cake, Eat It Once, Sell It Twice, and Keep as Little as Inspiration for the Next Cake. Tim.
Thank you, Malcolm, and thank you so much for the warm welcome also, Anna Maria. Really appreciate that. I'd also like to pay my respects to the Ngunnawal and the Ngambri people, the original custodians of this land, and enjoy sharing that privilege with them going forward together. I'd also like to thank Kira, Lisa and Hugh for putting everything on today. That was great. Thank you very much. It's, of course, an absurd title. I think we all understand that what I'm referring to here is not cake, but knowledge. And the open... Did someone work that out just then? You're not going to learn how to make a cake, I'm sorry. You know, open research, of course, is its own reward. And I think what I'd like to achieve, if I can achieve something here today, is to talk through the narrative of science and scientific discovery about how very diverse, interesting, wonderful teams have worked together and accreted other wonderful people along the way. My story is just one of those threads that you'd find through those different groups of people. And I think I'm using it in this case as a vehicle really to get back to what I think we should redefine translational science, translational research to be. Much more about that as we go. I do want to spend a little time talking about Ian Wark, but just a little. As Malcolm just pointed out, he was an amazingly accomplished person in his time. He was, if you read his quite long biography, a unique person. He obviously trained in the foundations. He was at the beginning of mass spec and some really revolutionary thinking about electrochemistry. So through his life, he saw incredible social and technological change, and he was part of those innovations all the way through that 20th century. He was an advocate for applied science, and I think that's probably how he's most richly remembered. But if you look at his foundational work, it really did go back to foundations. He really built on our knowledge of froth flotation, an incredibly important mining process, and electroplating. But in his manuscripts that he'd developed all the way through his life, he would always return to the basics in the pursuit of those applied and translational research objectives. He was a founding member actually of another academy too, which was the Academy of Technological Sciences, and that, I suspect, reading between the lines of his biography, that came about because there was a tension, an academic discussion about what constituted technology on one side and applied research on the other. And that was a live debate even when I was a young student. What was applied science? Where did it become technology? And I think that's a bit befuddled by recent funding rounds and other things I'll comment on shortly, but it really does implicate how we consider translational research. So I suspect that narrative which happened in this academy, that divide between the thinkings, the need to classify things, always our need to classify things, led to the Academy of Technological Sciences. He also was, not only was he considered a part of communities, he was a community builder, but he also built a structure within a very important organisation, CSIR at the time, to become CSIRO. And that was the Division of Industrial Chemistry. And so that was a structural contribution he made during his career to a very important institution, which of course builds on foundations to apply and translate research. And then finally, I think probably the most remarkable element, and these are just the highlights from a very long career of his, was when he had a hand in, a pivotal role in establishing the colleges of advanced education. And at the time in the Australian tertiary education sector, this was a revolution. This saw the establishment of 50 institutions around Australia, and it was seen as a way of diversifying how people were trained through all sorts of vocational and higher educational programs. We've seen that, of course, transform a few times in our lifetimes, and I think for me, it's probably signalling that diversification of the education system is about to happen again. And more about that later, maybe. Before I go further, I really would like to pass on my loving thanks to my parents, Tom and Beres. Tom's here in person, Mum's online. Very lovely to have you both here. It would be remiss for me not to mention Kim Wilson, a high school science teacher, for all the inspiration and support he provided. And of course, a big shout out to my family who are actually here today too, to hear a lecture that's not a dad lecture for once, which is nice. So thank you for coming. I think, and the reason I dwell on those dedications, particularly around parents and teachers, is because, and we all know this, we all have the common experience that teachers and parents help us form, give us the language, help provide the opportunity where we can take the abstract thought and build arguments around the relatable world that we see. And they do that in a number of ways. They can help us look up and out by buying us a telescope, or look down and inwards at the cosmos using a microscope, whether it's maths or music or art or craft. These are all ways, these are methods to explore an abstract concept and make it relatable. So I think that's a very important, the reason I dwell on that very familiar topic that we all know well, is that it's one of the important elements of becoming a translational thinker. And the other thing, of course, is the ability to socialise, and that, of course, comes with school and sport. So all these things happen in a very formative way at a very early stage in our lives. Now I want to unpick and walk back translation. Much is made of translation, and I think in the context of our current funding agencies, it's synonymous with commercialisation, and I want to walk that back. That's not how it started, and I don't think that's how it needs to continue. At any time, a discipline informs another discipline in any arena and provides a different form of thinking. That's translation. That's the simple act of translation, and it doesn't have to be a scientific transfer. It can be all sorts of transfers. So translation is a fundamental human skill. It's something we learn from a very early childhood. But in today's context, in terms of the science that I want to introduce and talk about around the teams, that there are two dominant elements in my view. One is you've got to go to the fundamentals. That's where it all starts. And although Barry Ninham, who's a wonderful person and I think probably the smartest person I have ever met, most agile thinker, he said if you get the basics right, the rest will follow. He wasn't the first to say this, but it was the first time I really heard it. And the other thing, of course, which creates a dynamic tension is this ability to work in diverse teams. You know, we know it's almost a natural law that diversity breeds innovation. And I'll come back to that theme reoccurringly, as you'll see. But I think it's that dynamic tension that leads to real innovation. The Medici effect was also a pivotal time when someone actually told me something that was an aha moment. But I think to some extent Frans Johansson's idea about what that diversity creates innovation is only part of the story. And I think Barry's contribution takes us back to the fact that you need to focus on the fundamentals, because if you don't, you run out of steam. You start to eat your future. You can't just translate continuously. There needs to be a cycle of reinvestment of the foundations and translation. It's the tension that keeps that innovative. So, as I mentioned, my story is just one of the threads that could be woven through these diverse groups. I'll try and illustrate for you today. And I want to start with the fried egg. So that fried egg is any person who has a skill and a methodology. And me, I'm going to pick surface chemistry. What I like about physical chemistry is on that fringe between not quite physics, not quite chemistry. It's a nice place to sit. And my specific domain is surface chemistry. So everything, the material world around us is just interfaces. And interfaces are lovely because they're devilish. All the chemistry that happens within a bulk material is different when it's at the surface. Molecules that are at the surface manifest different structures and forces in ways that you don't see anywhere else. So surface is a very, very rich space to study. And with any discipline, there's always a methodology. In my case, it was microscopy, atomic force microscopy, I'll mention in a moment, but I could do a fried egg diagram for nearly anyone in this room. And the important thing isn't to do one fried egg, is to show how the fried eggs overlap. So in my case, because I work naturally at the interface of different disciplines, and you can see a range of topics that are things that I've encountered over my career at least. More recently, computed tomography was another methodology that brought me into another way of thinking, and I'll talk a bit about that. The three purple topics that I've highlighted here are if you like, the case studies I want to walk through, because they all introduce diversity in slightly different ways of thinking, and why diversity does lead to innovation. Good. Now, I owe a debt to Richard Pashley for inspiring me into surface chemistry. He was an amazing lecturer, is an amazing lecturer, and this is one of his famous slides. It's taken from a very old CSIRO applied physics journal, and it shows how back in the 50s, industrial chemistry was in a heyday in a way, and there were lots of methodologies being developed to try and explore how chemicals had effect on the material world. In this case, we're all quite familiar with how detergents work. Detergents, of course, allow oil and water, which don't normally mix, to be solubilized and dispersed amongst themselves. And so this was a novel test for testing the detergent, quality of a detergent and the ability for it to strip the grease off the feathers of the duck. Now, those who are Monty Python fans will know, of course, why ducks float. Of course, we are all wrong. They float because of the air trapped within the feathers. And in this case, if a duck could look depressed, I think that duck does look depressed. And the reason I think Rick illustrated this to us, showed us these slides, was primarily this, that everything that's happened to that duck on a macroscopic, if you like, a duck scale, happened because of effects at a molecular scale. So the combination of very subtle effects happening at the molecular scale spread over the vast surface area of the feathers in interface with the air led to a macroscopic effect. And that's sort of a philosophical perspective for where surface chemistry leaves us thinking. And to give you a sense of a better sense of how a surface chemist might think, particularly this surface chemist, I want to just take you quickly through and ground your intuition in the way we think about scale and the forces that exist at that scale. So human hair in relation to a printed dot, the smallest you might print at home on your printer, to a blood cell, to a bacterium. Now that's a linear way of thinking about size. And there's a more constructive way to think about the vast microcosm that's under a microscope by looking at powers of 10, of course. So as we zoom off towards the to the left, we see we're getting closer and closer to atomic scales. And I've put those four familiar objects on this scale to show that actually when you plot them in powers of 10, these vast length scales over 9 orders of magnitude get compressed conveniently. If we look at other familiar objects, such as, and I'll talk a bit about nanoparticles or colloids and macromolecules, you can see they can fall conveniently on that microscopic realm. But probably what's most exciting, what gets me out of bed as a surface chemist, are the surface forces. And these are the forces that are manifest at the scale below about a millionth of a metre, about a micron, and they're a consequence of the thermal motion of molecules in combination with very specific quantum effects. They give rise to an amazing array of forces that emanate from surfaces at a molecular scale that clothe and decorate everything we see. Sometimes they're attractive, sometimes they're repulsive, but there's a myriad of forces and there's an endless combination to study. So if we're going to talk about forces, I need to give you another bit of intuition, and that's of force itself. And Newton, of course, gave us a lovely chance to consider what, and hold in our minds what a Newton of force might be equivalent to. And you think of an average apple, a 100-gram apple, hold it against the force of gravity, and it takes about a Newton to hold it steady. If we go down 3 orders of magnitude, in that case to a millinewton, it's 1,000 times smaller, it's about 2 drops of water. The weight of 2 drops of water take about a 1,000th of a Newton to hold still. A millionth of a Newton is about the weight of an eyelash, and then a billionth of a Newton is about the strength of a chemical bond. And it doesn't really matter what bond you're talking about, whether it's diamond or graphite or anything. It's all around about a nanewton. What makes bonds so different, in effect, is their geometry. And I won't talk about that today. But in principle, a surface chemist starts to get very excited around the nanonewton scale and a little bit below. And some of the beautiful forces that are manifest below a nanonewton, hydrogen bonds, for example, confer amazing properties to things like water. And again, a lecture into itself. Now, a surface chemist does have a technique. The mainstay technique now is the atomic force microscope. When I started, that was a very new technique. And I want to tell you a little bit about what it does, because it is a microscope in every way, but it doesn't look at a surface in the conventional way that we might use light or electrons. It feels a surface. It uses the surface forces that are manifest at the scale of molecules to give you a sense of the topography, the texture, the molecular texture of a surface. So it's a very simple technique. It's a beam that's flexible with a sharp stylus. A laser beam is focused onto the free end and reflects off at some distance. And any small bend or movement in that cantilever is magnified by the virtue of that distance, and that spot can be measured and related back to the actual minute movement of that cantilever. So then the simple task is to move a surface underneath that cantilever and to measure the deflection or the force acting on it at a molecular scale. And on the image there you can see a spaghetti-like blat of DNA molecules. And so that really highlighted how the technique came into the lab as an imaging technique. The other thing it does, of course, is that you can apply a higher force to break those bonds. And what I've shown here is a consequence of doing nanomechanical work, where I've scratched in the shield of coat of arms of the ANU. It's about the size of a red blood cell, to give you context. So up close, the needle itself is generally something like a pyramid or some other structured tip, and that's the tip that does the imaging. Together with William Ducker and Rick Pashley, we conveniently stuck things that were about colloid-sized onto it. And so all of a sudden we weren't just looking at surface topography, we're able to use the surface forces inherent in the systems we're looking at to study those systems themselves. So I'm giving you this sort of colloids view of the world from a surface chemistry perspective to give you an idea of why these foundations in this sort of work would become important for where we would go next. So in looking at these forces, we could apply different levels of force and come closer and closer to a surface and see different parts of how that surface was structured with the prevailing surface force in that environment. Now, the beautiful thing about doing open research is that you never really know who's going to read it. And the great delight, I'm sure we've all had to many extents, is going back to literature to see who's actually quoting your work. And it's sometimes groups that you may not have originally designed the work for. The other thing we did was to go back to macromolecules. We took the particle off the tip and we just used the tip to hunt around for stray fragments of macromolecules, of polymers, and then to tease out, as if we were fly fishing, a tether or a loop of that polymer and stretch it. Now, when you take a randomly coiled polymer and stretch it, what you're not doing is straining the bond angles. These bonds around in the molecules are free to rotate. And as you stretch, you're straightening the chain and taking the kinks out. You still end up with a zigzag molecular chain. The force required to bend those angles is usually high enough that you're going to break the bonds. And so this is a very interesting way of getting at the thermodynamics, the nanomechanical work at this scale. And we could measure the loss of degrees of freedom and the acquired entropy or loss of entropy in these tiny molecular, single molecular experiments. And again, that was research done for research's sake. That was a beautiful experiment to be done and to be published. It informs, of course, other sorts of thinking. And these are the sorts of things I want to describe today. My talk is much less about the science I've done. In fact, of science at all. It's really about how science can be done. And I want to draw on three experiences. They're connected through diversity, the topic of diversity, but from different perspectives. The first is nanoparticles. So this was a really lovely time that lasted well over almost 25 years. Primarily led by a very brilliant inventor, Bill Burch, who I've circled there on the screen. Bill really should be given huge accolades for the work he did. In the mid-80s, he developed a technique called Technigas. It's a diagnostic technique. It's used worldwide in more than 40 countries. It is, in effect, a radioactive smoke. And that's basically what he designed and set about trying to build in the 80s. It is credited with saving hundreds of thousands of lives around the world because the primary aim is to image the functioning bloodways of airways of a lung, a damaged lung, particularly a lung that's got a pulmonary embolism or some other defect in it. So Bill developed this technique where the patient would breathe in the radioactive gas, stand the patient or sit the patient in front of a gamma camera, and the radioisotope emitting gamma rays would produce an image, a functional map of the airways of the lung. It was an amazing technique and amazing discovery. Now, Bill knew that he could do much more than imaging lungs, and he set about to develop a very diverse team to try and explore, first of all, what was the particle, what defined it, what was the structure, and more importantly, how would it could be used for other applications. So you'll see on that in that photo slide, there's a range of people that you might not normally meet in the lab. Electrical engineer, inorganic chemist, nuclear physicist, gastroenterologist. And this group was the seed group that would grow further. We quickly discovered that the particles were a very interesting combination of graphite and technetium. So technetium is an artificial metal, it's a gamma emitter, it's one of the most common radioisotopes for diagnostic purposes in the world. And in this case, the way it was fabricated would leave the particle wrapped up, shrink-wrapped in graphite. Now, graphite is chemically very inert, and so in the milieu of the body, particularly in the lungs, there was no way that the body could get to the technetium. The technetium was locked up behind the very thin layer of graphite. That gave us an idea to work further and develop techniques for not only inhaling but injecting, ultimately to inject these particles. We didn't know where we were going. We knew that the graphite would have some affinity in the milieu of the body, but we didn't know what that might be. Rod Brout's shown here is another wonderful inventor in that team. He developed a technique which allowed that smoke to be captured in a very small quantity of liquid for injection. A lot of surface chemistry went into this, different methods for absorbing molecules to the surface of the graphite. All these things were actually for naught in the first instance because we discovered very quickly, thanks to Gary Buffington and Harry Nye, that graphite has a very strong affinity for clots themselves. So rather than imaging the clot by inference in the damaged lung, the idea here was to try and inject the technique gas, now called thrombotrace, into a patient and let it circulate through the body. And the graphite particle had a high affinity for active blood clots. So that was firstly some lab work that led to a clinical trial. It was very interesting. There's a long story behind this, and you'll get me, I'll say this a few times, there are lots of long stories behind this, but it was the first time that we had a chance to really explore how the role of surface chemistry in the way of attaching nanoparticles to functional or target organs in the body. Very quickly we could see that the team needed more diversity, and Ross Stevens was invited in the group. He had a strong background in haematology and cancer biology, and he quickly grew the group even further, bringing into it biochemists and veterinary surgeons and all sorts of people, and most importantly, one of our strongest industry partners, Certex. Now, Certex was very interesting. They could wait for a discovery and a development. They weren't pressing for products. They understood that we need to go, in many cases, back to why particles were doing what they were doing, and in fact, even to invest in novel isotopes and particle production. So there was a lot of patience in this relationship that allowed for us to focus on the fundamentals, then look for translation. But I guess at this point I'm highlighting one of the sorts of diversities that you'll see throughout the talk was, in this case, you might not normally see this collection of people from engineers to biochemists in the same group. But Ross certainly had a vision, and together we shared a number of developments around a host of nanoparticles. As the group developed, we bought many gamma cameras, and Ross is seen here on the left, bottom left, in one of our most recent gamma cameras. And it gave us very exquisite images around functional aspects of the work we're doing. So when I talk about function, there's two ways of thinking about imaging. There's structure and there's function. A gamma camera, something that's based on nuclear medicine, will give a functional view of the disease, typically, that you're trying to look at. Typically, you can locate where the disease might be, but you won't have high resolution. It's not a structural image, but it is a functional. It's a consequence of doing of some biochemistry or some physiological activity. So that got me thinking. This group got me thinking in parallel with how three-dimensional imaging could be used both in functional and structural settings for applications well beyond the clinical case. I've highlighted some of the successes for that group over time, and I think it's important to highlight, while there were patents and clinical trials, the things that were very directed to applied outcomes, there are also publications and a long investment and a commitment from the partners and staff around novel developments, particularly in engineering. So this is a segue into structural imaging now, and I owe a lot to this installation art from Tim Noble and Sue Webster. And here they've collected a collection of junk and chairs and all sorts of things and shine a light on it. And if you look at the projection, you get a very unusual effect. Now, that's by design, of course, but it's our intuition that's jumping in and saying, oh, there are two people sitting on the steps, and that's incongruous with the way the junk is arranged. It's just simply a question, it's a trick of perspective. And in this case, if I'd just shown you the silhouette before I'd shown you the junk, you might have expected two people sitting on a step. And that sort of highlights a couple of things. First of all, your intuition can make assumptions very, very quickly, and you always rely on more than one technique. But equally, if I'd just shown you silhouettes and said, well, now I'm going to irradiate with X-rays, then you might have been led to the conclusion that that is a plausible image from that structure of junk, and it isn't, of course. And this highlights another aspect about imaging, is that not only does our intuition jump in and teach us a lot before we have a chance to stand back and look at it, we also assume dimensionality. So in this case, we're looking at what's clearly a two-dimensional projection, but because this is a familiar object, that image, the radiograph of the skull, we can easily interpret in terms of 3D. We abstract this image just as those kids did back with those microscopes and telescopes. We're abstracting right now and using the familiar to inform our guess. But X-ray tomography aims to remove that ambiguity that you see in a 2D projection by restoring a faithful reproduction of a 3D object. And it's quite if you like, in a classical sense, in a conventional sense, it's a simple process of taking many, many different perspectives. Here you see rotating radiographs. And again, our intuition jumps in and tells us that is actually a three-dimensional skull of a lizard in this case. It's not, it's just a series of 2D images, but our perception has, of course, robbed us of the interpretation. In conventional tomography, of course, you can take different views. And the trick here, back in the 20s and then in the 60s, Radon and Hounsfield developed, first of all, the mathematics and then the engineering device for realising what we're seeing here. So a projection, a radiographic projection taken in series of different independent views can be inverted and reconstructed back into a faithful representation of that 3D structure. Here I'm just reconstructing one slice through an object, but those slices can be played in sequence, and you can see very quickly that there's an impression that this is a three-dimensional object, slice-wise through here. Now that's conventional tomography. The group didn't stay with conventional tomography very long, but I'll talk about that in a second. For those who young in mind might have guessed those sequences already. This is just a common pill beetle or a slater from the garden. But tomography really does give that opportunity to look at and remove some of the ambiguities that something like a radiograph might produce. And of course, you're looking at internal structure, so all the way the muscles and the carapace are connected can be recovered in a very complex, very beautiful way. So that's tomography, and that was part of the technique that started in nuclear at a very interesting and really the most diverse group I've ever worked in applied mathematics, Barry's original department. It was motivated by a dream that Mark Naxted's shown there had, where he thought that if you could develop really faithful tomograms of objects, complex objects like rocks and bones and all sorts of things, that would be a way of developing an understanding of a framework that you could do physical simulations on. And I'll show you an example in a moment. But for the moment, I just want to focus on the team. You can see here, this is an unusual connection of engineers, scientists, and technicians working around problems that were at the interface of biology and physics and biology and materials science and geology and so on. It was an opportunity that I think probably couldn't have arisen in many departments at all, but it was Barry's original vision to keep a department diverse that allowed this opportunity to happen, in fact. Now, I'd said this is a snapshot of the group back in the early 2000s. The group now shown there is 3 times larger today. And it happened around about 2009, 2010. We had developed a very large industry consortium. 23 oil and gas companies were helping us build some of the foundations required to use tomography to develop that framework to inform petrophysical and other sorts of simulations. As I say, I'll get to that in a moment. I want to focus on the people because back in those days, this was largely the original founding group. Now, since that time, people like Andrew Kingston, Mark Naxted, and Adrian Shepherd have grown and built on these foundations like cities on cities. And the groups and opportunities have grown enormously from these early days. Many of those stories are for them to tell, but I did want to highlight that diversity begets diversity. So what were we doing? This was Mark's vision. Mark's vision was to take a faithful reconstruction of an object. In this case, you see a sandstone. You can see the pore space in the sandstone, and in that pore space, a computational model has been run which allows us to look at the fluid flow, the fluid velocity through those pores. In this case, you see the high velocity fields, and then as it fades to the blue, you'll see the low velocity fields. But it captures in an instant what you can do virtually on a computer that could take hours, days, or even months in the case of this rock in a laboratory. And in many cases, you can do experiments that aren't possible to do by virtue of the fact that you have an accurate three-dimensional framework of that complex structure. Many stories can be told about those simulations, and I'll park that for another moment. But one of the opportunities of working with the oil and gas companies was that we were developing tools that would implicitly help them make decisions about securing that precious hydrocarbon resource. And one of the service companies that came out of this was Lithicon, mentioned earlier. I don't want to talk too much about Lithicon, except that it was a training ground for the way we think about doing research and translating research, and still keeping enough of the research in the university that you can have your cake and eat it too. And I owe a great deal to Mark Naxted and Victor Pandano here, who really explored those novel ways of how industrial partnerships can inform, help, and even build the foundational science and turn back to the foundations that the group needs to sustain itself. So there was a lot of lessons learnt in the around 2010 to 2015, and some of the headlines from that group and from that period might stand out to you. I've shown them here just to illustrate again that there's the 500 publications are a sign that the group was always focused on the foundations and open research. The $80 million of commercial sale of Lithicon illustrates actually there was a big ticket item in that sale. But to some extent, neither of those two statistics really drive home the value of commercial exchange as much as, I think, the bottom one, the $50 million of research income that the group has earned over that time and continues to earn and grow because of the foundations that were built right at the beginning. The team is much more diverse now. And I really have to focus on why that was enabled. It was enabled by very new thinking in our technology transfer office. Credit to Fiona Nelms and again Victor Pantano for having enough vision and agility to think about how we preserve the research environment and still translate into the industry setting. And some of those lessons have been many of those lessons are now informing the way ANU does tech transfer. I think we've had a long legacy and built on those successes and sometimes fresh thinking around how to do that. The leadership there is terribly important. I do pay great respects to Jim Williams, Lawrence Cram and Ian Chubb, because they understood intuitively that strategy isn't always top-down. There's a bottom-up aspect to strategy, and they had enough vision and foresight to see that Mark and the group had something that was novel, and they supported it. They broke a few models in doing this, and with that, I think we evolved a very mature way of how to deal with tech transfer at the ANU. One of the consequences of that transfer was a return back of some of the commercialisation returns to the university, and in that process we established two foundations, one which nods back to a visiting fellowship scheme which turns to the foundations, and of course the translational aspect in a technology development fund. So they're enduring gifts of that commercialisation. Now, I wanted to talk a bit about the fossil resource because it is a way I got back to my childhood in a way and started to see diversity again in another different way. And working with paleontologists, I should stop and say, working with the X-ray microscope, with the tomography facility, I think all my colleagues in that group would have had a similar experience where all of a sudden you have a new technique that other disciplines really would like to get to and use. And that gives everyone an opportunity to look inside complex, precious objects. Fossils are a great example where you can't just cut them open and have a look at the auditory system of a fossilised whale. You can't do that. They're too precious for that. And so, like all my colleagues in the CT group, we've become friends with many, many different disciplines wanting to explore this new form of microscopy. So I'm not going to talk about paleontology specifically, but I do want to mention that my focus was really brought into around Devonian fish. And what was lovely about working with the paleontologists, they also gave me this concept that if you have the right rock, the right environment, and then the right exposure, it's a metaphor for how research is done in general. So the right rock, of course, is that it's a sedimentary rock. The right environment is the right environment that causes fossilisation to occur. And then the right exposure is that at some time in the future, that rock is again at the surface. And Devonian period was interesting because the complete vertebrate form that we see today, that we walk around in today, was largely set in stone, set in motion at least, back then in that Devonian period. And I owe John Long a debt to this image that shows that actually our modern skeletal form really has its origins back in a fish. And everything you could take from a fish at that time, you could map every bone to the bones in our bodies today. The paleontologists were incredibly generous and took me around the world, from China to Gogo to the Sturt Desert and also to Antarctica. I owe them great debt because their diversity was in as much as that they considered geology and evolutionary biology in the same breath, but they were in the pursuit of diversity. The diversity was that natural history and the life that would evolve into what we see today. One of the discoveries that, one of the many discoveries we had when we had access to a tool like the X-ray microscopy, the tomography, was to look at soft tissue preserved within these very special cases. And it gave a chance to meet David Attenborough, a career highlight, but also primarily to refocus and look at other specimens that had been previously studied, and we've discovered many other embryos and other soft tissues since that time. It was a change in perspective. No longer were we thinking that only bones were preserved, the soft tissue was also preserved. And I just want to wrap up with actually a couple of slides, and I think it would be remiss of me if I didn't mention Antarctica, but I could bore you for hours with pictures from Antarctica. But I'm very grateful to the paleontologists who, in their pursuit of diversity and the study of diversity, have led me to different ways of thinking about that open kitchen that I mentioned in the abstract. The open kitchen is also the field. And sitting around the campfire, in this case huddled around a warm heater in Antarctica, many discussions about how different types of science would influence the evolutionary thinking came about. I just want to finish with one slide here. I know I'm close to the time, but it's not an end, it's not a solution or a recipe to how diversity is important. And I think as I keep coming back, the diversity is only part of it. The fresh thinking around the foundations is also important. And at least I would like to suggest that there's a rule of about 2 to 1. You should spend about twice as much time focused on the foundational research as you do in translation. And for me, that's obviously not a metaphor, it's not a rule for an individual, it's a rule for an organisation. And particularly an organisation can work at a big enough scale that spontaneous ideas can find a home. That's very important because ideas come up at all times in conversations, but they need to find a chance to be exemplified. I think keeping boundaries is very important. Keeping boundaries porous is very important. They should be dynamic and shifting. Always invite people in and really be prepared to risk a little time to explore crazy ideas. Recognising partnerships at all levels. And I make this comment because in my new role, which is further from research, I've used all these techniques for building partnerships and collaborations with professional staff that work endlessly, tirelessly to keep us on our academic missions. So those partnerships are very important, and I think it's important also to recognise that in the university we build stuff, we break stuff, and the technical workshops and the open facilities that allow all these active new areas of research to be developed are terribly, terribly important. I think I'll finish there because I'd like to thank, of course, the Academy very much for the honour. I was saying to Malcolm, I think it's my first award. I'm very proud, thank you very much. But I also need to thank the Australian National University. It's been a wonderful open kitchen for me for over 30 years. It remains an amazing place, amazing compact university to work in. Disciplines from humanities and sciences can easily integrate. And I think that's something we should preserve for the future. I'll leave it at that. Thank you, Matt.
So thank you, Tim, for, I think we'll all agree, a wonderful lecture, spanning distance scales, time scales, disciplines, techniques. But the thing that I guess was most prominent for me was that how people were at the centre of everything you've done. Talented people, but also leadership in people, which was wonderful. So I'd now like to throw it open to questions invited from the audience. We have some mics here if you want to put up your hand, but also those online can submit by scanning the QR code. There you are, which is on your screen, and we'll pick them up and insert them into the mix. So, who would like to ask a question for Tim? We have one here. I think we're second, yes.
Tim, you left us hanging. You said it's great to go back to the research and see who's cited you. What were the most surprising ones you've had?
I think the ceramics industry is probably the most exciting. So the early work where we looked at how, the early work where, have I got that? Okay.
Come here.
Excuse me. Just turn that off. I think the early work we did, we were looking at forces between surfaces and being picked up by the ceramics industry and done good. That was surprising. We couldn't have imagined that we were working for that audience. So I think it's a lesson about speaking openly and not prejudging the way people might see your work, really keeping it open and fresh. It's hard to do. Sometimes we write a paper with a particular audience in mind, and where we can, maybe it's sometimes better just to hold that bias back and write for a general audience. So yeah, that's one of those things. I think also the nanoparticle work has been revealing in that it's not only the medical and clinical applications that it's been picked up in, it's been picked up in environmental research as well.
Thank you. Do we have a question there? Yes? Yep.
Thanks, Tim. That was masterful. Just the last few days, I've been listening to some podcasts about AI and people's thoughts about where it might be going and what the risks are. What in these kind of areas that you've been talking about, is there a role for AI to play to just dramatically expand their possibilities? And kind of independent of AI, where do you think this field is going if you were to project out 10 or 15 or 20 years into the future?
Yeah. So I'll probably contain the AI comment to microtomography, and the answer is it's been a revolution. But I think that's a truism across many instrumental techniques. Anywhere there's complex patterns complex patterns and weak signals in those complex patterns, then I think AI performs extremely well. Mark and Adrian are leading work where they are not only using AI to classify materials in 3 dimensions to differentiate, or group like materials together in a complex structure, but they're also using that to inform how mechanical processes might evolve. So AI doesn't replace the physics or the chemistry or the expert, but it does take the drudgery out of a lot of decision making. And in the case of the oil and gas work, a lot of that original analysis in 3D was done manually. It was done with very sophisticated computational tools that Adrian Shepherd and colleagues developed. But now those things can be done fluidly and effortlessly on larger volumes of data using an appropriately trained machine learning algorithm. So look, it's a revolution. I don't fear things like ChatGPT. It's another tool. It's another way of collating data. You always have to be mindful of what you're looking at. It's a bit like the picture of the people sitting on the stool. That's a silhouette of something you think are 2 people sitting on a stool, but it's not. It's a pile of junk. And I think maybe that's a strong metaphor for AI. Be careful of what you're looking at.
Did I see another one here? Yep.
I was intrigued by your comment that the nanoparticle, or the graphite-covered one, had an affinity for blood clots.
Yeah.
And is that a hydrophobic effect, or how can you explain that?
So strictly speaking, without getting into too much, it's not graphite is not hydrophobic. The contact angle water makes on graphite is less than 90 degrees. So it's very close to 90 degrees, but it has some weak affinity with water. And we'll talk why that is. I think it's the pi bond interacting with the water dipole. But why does it interact with the fibrin is not well known, but it has been known for a long time that carbon in general, if it's the wrong type of carbon, can be thrombogenic. It can create blood clots, in fact. And what we proved very quickly was that injecting these particles didn't create blood clots. Graphite's unusual in that it has an affinity but not a thrombogenic activity. So it's not clear to me why that's the case. No.
We need the basic research.
We do, yeah, of course.
Hans?
Thank you, Tim, for such a brilliant tour and showing us how things are connected that we might not see as connected in the beginning. And you pointed out a number of really great personalities who saw connections well ahead of their time, and they might have never written it down. So for the future, are we good in finding these personalities, nurturing them, making use of them? Can we do better?
We definitely can. I think if I looked at, Ross Stevens, Mark Naxted, in particular, let's just pick those two wonderful individuals, and Barry Ninham, there's another one, a case. I think what's true is that they've really had the freedom of their kitchens. They've not had the time pressure to deliver milestones. They've not had an ambition to be the best in a particular research category or anything like that. They really had time to sit and think and cogitate, and to meet like-minded. So I think that there is a huge risk that universities are losing that strategic imagination. So there's no recipe to this, but you do have to give creative people the freedom to think, the freedom to mess around in the kitchen. So I think that's where I'd stop short with defining a recipe for it. It's about freedom. It's about intellectual freedom, and I think universities have for a long time provided that environment, but all sorts of other constraints, including the way grants are structured, for example, lead us down a pathway of not being patient with our research. Trying to hurry along, and you can't hurry a creative process. So people like Mark Naxted in particular have taken the very, very long view and trusted the people around him. And I think an institution that respects that sort of ground up strategy setting is the institution that will always do novel work. Yeah, I think it's as simple as that.
I can hear the round of applause online on that one. Wendy, yes, you've got someone online?
I sure do. Good afternoon, everyone. I'm Wendy Wark Lecture. I'm the Communications Manager at the Academy of Science. Related to Hans's question, we've got a question online for you, Tim, from someone watching on Ngunnawal country. And it's, were there any unique challenges in your pursuit of translational research, particularly working with a diverse group of researchers or even with industry?
So that's a question where I always answer that the challenges are sociological, not technological. So yeah, look, it's each of those slides probably has a lecture behind it. And so one of the lectures I like to talk about is how the group, which had always imagined itself as a fundamental group for 10 years or more, developing novel imaging techniques and then novel analytical techniques, computational methods and so on. That was a group that was really inspired by, as I said to Hans, people like Mark, that long view, that deep vision. And then a partner comes along, like an industry partner, who has an end use and a specific need, and that then focuses the group down that pathway of delivering that specific need. And that's a natural tension between going back to the foundations and being broad thinking to being narrowly focused. And I think that does cause tensions in a group. As you learn each other's methods, I think those tensions ease, but it's something that should be spoken about up front, and talk about who's going on the pathway and who's going to, contribute to the foundations. I think they're important things to talk about in any big group. And they're discussions that happen more fluidly the larger the group gets, in my view, because you naturally find people who are predisposed to translation or predisposed to foundations. And then, leaders like Mark and Adrian and Andrew Kingston and others, they really set the scene for how those different aspects of the group interact. But doing things at scale, I think I'd add that to my comment to Hans, is that things have to be done at scale for spontaneous research-led, discovery-led research to work effectively towards translation.
Thank you. So I think we have one more. Okay, last one up there. Thanks.
Thank you very much for a fantastic lecture. I just want to ask, so one of the things that you mentioned is that the beauty of fundamental research is that you never know who's going to pick it up next, where it's going to go. And I'm just curious to hear your thoughts about how much you think the discoverer or the inventor should feel a sense of responsibility if their technique or technology later gets used for purposes that they don't think are particularly ethical or have turned out to be bad for society. And I just wonder this because I know a few nuclear physicists who've felt like they need to atone for what their field has done. And I don't really know if, I kind of feel a bit sorry for them because, it's not like they actually did it, but I'd love to hear your thoughts on this. Thank you.
Thank you. And it is a topic I think a lot about these days, I have to say. I think when you're doing open fundamental research, the next step is usually not a destructive step. They're many steps away from where you publish typically. And so I think the reality of publishing openly in foundational research is that you're not necessarily close to dual use activities. But that's not to say that people don't have regret. And certainly one of the founders of this place, Mark Oliphant, is a case in point. He would at times say that what he did during the war was for a war and it was in that context, but in peacetime he could see the atrocity that it was. And so, I think that's an individual's path. How much people should reflect upon that, I think it's an important thing that scientists are taught ethics and the consequences of actions and all those. Science is just part of a society after all. Scientists are no different from anyone else in society. But I think the practicality of open research is that you are very often very far from dual use, and so it's many steps before it can become harmful. It doesn't mean that the individuals don't relive what they did initially. I mean, and you might find that the founders of CRISPR and things like that do have moments in the future where they think, wow, what have I created? But that's a very personal step. We can help those individuals by considering ethics up front. That's true. I take your point.
Okay, so we've got one final one at the back. Thank you.
So you talked about the intellectual freedom. So the more I talk to the PhD students, I feel that there's a lot of pressure about publishing in top journals. So like in the early stages of research career, like how should one keep that intellectual freedom alive? Like how to keep that freedom of thinking in the early stages? Yeah.
So I'm a strong believer that a university should enable their students to own their IP as the default case. It's not to say some students don't come into groups that are predisposed to commercial realities, and so that's a different context, but in general the default case, students should own their IP and become masters of their developments. That's the whole point of a PhD in a way. But I think what I heard was the question was the pressure to publish. I think there should always be pressure to publish. I think publishing is the best way we can get our ideas out there. I think there should be no constraints on publishing. And I think to the question about dual-use activities, it's one of the best ways to defeat dual-use activities is to publish. Have it peer-reviewed, get it out there, get people dissecting it and considering what the implications are. So I think for a student, publish broadly. don't publish in little pieces. Try to tell a big story or something that's, useful. But someone will find relevance for it. I mean, I think that's, again, I come back to comment, the great beauty of doing open research is that someone finds your work relevant. It's not just, you're not doing it for your own joy and benefit, although that's a large part of it.
Okay, so I think I'll just say one last bit. I'd like to draw it to a close there, but once again, congratulate Tim on his award and also for a wonderful lecture. Let's congratulate him again. So this will conclude the online part of today's activities, but I'll invite everyone in the room here for some lunch in the Jaeger room. Thank you, Tim.
Thanks, Mark.
Thank you. Cheers.